Hello everyone. In previous sessions, we have learnt principles of counting and also factorial. From here we proceed, and now a new topic we start, that is permutation. And of course some theorems which are related to permutation. So let us define first what is a permutation. And definition says that a permutation is an arrangement of the objects in a line unless specified. When I say unless specified, means in the problem, otherwise it would be mentioned. If it is not in the line, then what? If it is not mentioned, that means it is in a line. So a permutation is an arrangement. My emphasis is on arrangement. A permutation is an arrangement of the objects in a line. Now take one example to understand this. Now if I am given say 4 digits 1, 2, 3, 4 and I am thinking of arranging them. Few arrangements I have written. Mind you please, I am saying few, not all. Now I have written suppose somewhere 1, 2, 4, 3, or I have written it as say 4, 1, 3, 2, or I have written it as 2, 3, 4, 1, right? Now these are few arrangements. I cannot write all here. It is only for me to take your attention that you can place them in different orders. So order matters here, and whenever order matters, that means question is related to arrangement, and hence I would say permutation. Okay. Now let us take some theorems one by one. Now my first theorem is the total number of permutations of n distinct objects is n factorial. Now this kind of thing you had done in my previous sessions also. If I ask you to write some 4-digit number, say with possible digits as 1, 2, 3, 4, then I had written there like first place can be filled in 4 ways, second can be filled in 3 ways, then 2 ways, and then 1 way. That means 4 into 3 into 2 into 1, which is nothing but 4 factorial. So we had 4 distinct digits. We were asked to make 4-digit number. In how many ways it can be done? My answer was 4 factorial. Same thing, without mentioning the theorem, I have already done once with you. Now let me do it once for all formally. Theorem says total number of permutations of n distinct objects is n factorial, right? Now theorem 2 is, now I am not getting into proof part, please, because that is not required for examination, competitive examination. Now let me take theorem 2. Theorem 2 says that total number of permutations of R objects taken from n distinct objects is, and answer is n factorial upon n minus r factorial, and obviously r is somewhere between 1 and n. It can be n also, it can be 1 also. Now how it is different from the previous theorem? Previous theorem said that you were taking all n objects, right? So n factorial was the answer. Here I am saying you take r objects only out of n objects. Not all are to be permuted. Not all are to be arranged. Only r objects are to be arranged. Means what? That if suppose you are given 5 digits, say 1, 2, 3, 4, 5, and I ask you to make a 3-digit number only, then what would be your answer? Your answer would have been 5 into 4 into 3, right? First place can be filled in 5 ways, second can be filled in 4 ways, third can be filled in 3 ways. So 5 into 4 into 3. Of course, I am assuming here no repetition allowed, right? So 5 into 4 into 3, this part I could have also written as 5 factorial upon 2 factorial. That 5 factorial upon 2 factorial, I can also write as 5 factorial upon 5 minus 3 factorial. So that is what we are doing here. N factorial upon n minus r factorial. What is r? R is number of objects which are to be arranged, right? So let me proceed from here to the next. Before that, once for all, I write that what we mean by NPR. NPR is actually n factorial upon n minus r factorial. That's a new notation for you. So you will have to remember. NPR is mostly used. Other option in some of the books is also written, so I have also written n, and then inside bracket you write p comma r. Now from here I proceed to the next theorem, and the next theorem is that, and this is related to when all objects are not distinct. I'm sure many of you must have thought that if objects are not distinct, then what? Then we have theorem for it, right? And the theorem says that there be some A1s are there. How many in number? N1. There are A2s. How many in number? N2. Understand this. When I say how many A1s are there, that means A1, 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 like that, repeating N1 times. A2, 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 like that, repeating how many times? N2 times. That is what I mean here. When I say there are N1, A1s are there, N2, A2s are there, and lastly I have written NK, AKs are there. So in all, how many are there? N1 plus N2 plus N3 up to NK, right? That would have been the total number. Normally, using first theorem, if they were distinct, my answer would have been simply n1 plus n2 plus n3 up to nk factorial. But that is not the case here. Now what happens here? Since a1s are repeating, so what happens, even if you interchange two a1s, no new arrangement you get. That is why many arrangements get repeated if you write your answer simply as n1 plus n2 plus n3 up to nk factorial. So this cannot be the answer. Since each arrangement wherever a1s are there gets repeated, so we need to divide by n1 factorial. Similarly, wherever a2s are repeating, that we will have to understand that again arrangements are repeated, so we'll have to divide by n2 factorial and so on. So my final answer should be n1 plus n2 plus n3 up to nk factorial whole divided by n1 factorial, n2 factorial up to nk factorial. Now this is regarding whenever elements are repeated, or I should say elements are not distinct. Okay, so this particular coefficient is called multinomial coefficient, which again may appear in some other chapter also. So once for all I have written here. Now I go for properties of NPR. Now my first property is NPN equal to n factorial. How many of you understood how I have written that? NPN. NPR was here, R objects are to be arranged out of n. When I say NPN, means all n are to be arranged. And they are all are distinct. So answer should be n factorial using theorem 1. Okay. Now I go for next, and that is NP0 equal to 1. Now what was the answer for NPR? It was n factorial upon n minus r factorial. In place of r, what I have written here? 0. So n factorial upon n factorial I will get. So my final answer is 1 here. Now I go for one more, and that is NPN minus 1. NPN minus 1. Expected answer is actually n factorial. Why I am saying so? Because n minus 1 places you have to fill. Now you start filling one by one. N into n minus 1 into n minus 2 up to, now instead of last as 1, you will get 2. So even if I write into 1 further, no change will come. So it can also be understood as n factorial straight away. Another way of understanding could be that you are going to fill n minus 1 places. That means one object is not going to be used. Rest all you are going to actually fill. So which object you are going to leave? So again n options are there. So first I decide which object is to be removed, which is not going to be arranged. Correct? So I can do that in n ways. My subtask is n ways. Correct? And my next subtask is, now I have n minus 1 objects left with me, and I have n minus 1 places also with me. That can be done in how many ways? Arrangement. Arrangement can be done in n minus 1 p n minus 1 ways, which would be n minus 1 factorial. And this was one subtask. And one more subtask was that which element is to be removed. That also can be done in n ways. So my answer should be n into n minus 1 factorial ways using multiplication principle. So answer finally would be nothing but n factorial. Now this was regarding the properties of NPR. I go for illustration now. I think it's high time we must go for illustration. Find the number of numbers formed from 2, 3, 4, 5, 6 using all of them and without repetition. Now this question is regarding your first theorem, where all of them are to be used, means no second theorem where R objects are to be arranged out of n. That is not the case. All are to be used, and we can use it either by multiplication theorem, what we have done in the beginning, or by theorems also. Choice is entirely yours. Theorem 1 is applicable here, I am writing, because repetition is not allowed and all are to be used. And my answer would be, straight away I can write, that is going to be n factorial, means here in this case I will be writing 5 factorial. 5 into 4 into 3 into 2 like that. Finally my answer would be 5 factorial. Now this question is regarding theorem 1. Now I go for one more, and my next illustration is find the number of words with or without meaning which are formed from all the letters of word mobile. Mobile is the word M-O-B-I-L-E. These letters are to be used and all of them are to be used. Simple. M-O-B, 3 letters. I-L-E, another 3 letters, means total 6 letters we have. So answer should be nothing but 6 factorial. Can I write directly? You call it again whether multiplication theorem or you call it theorem 1. Now answer would be 720. Now before I leave from here, I must mention this to you that in this particular session I have taken examples only on theorem 1. Maybe in our next sessions regarding or related to theorem 2 or theorem 3, more and more questions will come. Till then, stay tuned. Thank you. Hope you have liked the video. If you want to subscribe, click on this side, and if you want to place order for the book, click on this side. Thank you.